Our software GiAPA is unique in many ways and offers novel features for monitoring and optimizing servers and applications. By demonstrating a few key functions, I hope to provide you with an impression of GiAPA's wide scope. GiAPA is an acronym for Global Eye Application Performance Analyzer, which exactly describes what GiAPA is: a tool for analyzing the performance of your applications, not the hardware. We leave that to IBM. This technical-oriented presentation will also reveal some of the unusual techniques used when creating GiAPA. First, a little background. The focus on developing performance-efficient programs is one of the fundamental building blocks in GiAPA. Many years of experience in application performance optimization as a consultant formed the basis for developing GiAPA. The idea was simple. GiAPA should enable programmers and operators without deep performance expertise to pinpoint reasons for application delays without needing assistance from external consultants. Another key objective was a light footprint, so data collection could run 24/7, and it shouldn't reinvent the wheel. IBM offered excellent tools. However, they focused more on hardware capacity than on application-level performance. Speaking of application performance analysis, most will agree that many consider it somewhat of a challenge. That a job has an unexpectedly high CPU usage does not tell where the programs use the resources. GiAPA collects the additional data needed to document what the jobs use the resources for. The result is a comprehensive database containing data for all jobs. Several powerful tools offer resource usage data collection. However, this is not enough to see where the resources are spent. When collecting data for all jobs in 15-second intervals, most jobs show no activity since the previous interval. For jobs having used at least 4% CPU during the last 15 seconds, GiAPA also collects data documenting the activity of the job. GiAPA has 4 features, which we think are unique. The first is the collection of resource usage data for all jobs, including data documenting the current activity whenever a job uses over 4% CPU. The second is the fact that data collection uses so little resources. Unique is also the comprehensive GiAPA database, being an extremely solid resource for analyzing system utilization and application performance. Most remarkable is maybe GiAPA's fully automated performance analysis of all jobs. Every 15 seconds, GiAPA receives accumulated resource usage data from the IBM Performance Collector API. By processing this data in real time, GiAPA can detect hotspots. We call it a hotspot when a job in a 15-second data collection interval uses so much CPU that it may have or cause a performance problem. The 4% CPU limit for hotspots is an installation parameter, which is the default today. Every time a hotspot is found, GiAPA calls other APIs to collect program call stacks and open files data for the job. The statistics, based on these samples of program and file usage data, document what the job uses the resources for. The hardest part of the GiAPA project was collecting all this data while keeping CPU usage low. Here is how we achieved that. Collecting the resource usage for all active jobs is cheap, because the data is kept in memory. Collecting call stacks and open file data is more expensive and therefore limited to when a hotspot is triggered. Our main concern, however, was IOs, since commercial applications typically spend more than 80% of their time on IOs. To minimize this, we implemented our own record blocking using a variable span format, and we compressed all collected data down to just 8% of the original IBM volume. The result exceeded all expectations. Our goal was to stay below 1% CPU. Instead, the data collection only uses 0.1%. How is a 92% reduction of data possible without losing any information? Here are some of the techniques used. GiAPA field lengths are in bits whenever possible. Example, file type, physical or logical, needs only 1 bit. A file is open for input, output, or update that requires 2 bits. We still have 5 more bits to go. All data belongs to a job ID being 26 bytes long. GiAPA stores them in 26 bits. For 10-byte object names, GiAPA uses only 17 bits. Long Java names require a bit more. Variable length records normally begin with a 2-byte length field. We manage without. These methods explain part of GiAPA's exceptional efficiency. A short-running batch job expanding and analyzing the collected data generates the GiAPA database consisting of over 20 externally described files. These serve as input for all GiAPA displays, graphs, and reports, and for user-defined queries and graphs. To reiterate, GiAPA's unique database contains 22 types of resource usage for all jobs and tasks every 15 seconds. Plus, whenever a job triggers a hotspot, active program level details down to source code line number, and file access data including the number of the current record. With all this data, you can solve most issues related to resource usage or application performance. The prerequisite for analyzing performance is, of course, data showing how the job was running. With GiAPA, you always have this data. Also unique is GiAPA's AAA, the Automatic Application Analysis, today the flagship of GiAPA. This example covers 40 hours of data collection. 100 minutes of runtime savings were found across 74 jobs, on average 1.5 minutes per job. By aggregating results per program across all jobs, GiAPA also detects optimization potential in frequently used short-running programs. Each case is presented on a single page, providing everything needed to assess and implement the improvement. And like here, often just a small code change is needed. Being the first and only software capable of fully automated performance analysis, GiAPA truly is unique. The logic behind the automatic detection of inefficiencies is based on a pattern recognition analysis of over 7 million call stacks received from servers in many countries. After 20 years of continuous development, often guided by user feedback, GiAPA has grown into a large product. The menu sections reflect the main areas: data collection and analysis, displays and reports, graphs, front-end to IBM's PEX and Trace, and database utilities, amongst others identifying unused databases and indexes. There are also SQL and query tools, data import and export functions, installation parameters, and housekeeping options. I will now show you two examples of GiAPA's original performance analysis, starting with menu option 15, Job Performance Summary. This selection panel, used for drilling into problem details, was originally GiAPA's main entrance for analyzing performance issues. You select a focus area between 16 different sort criteria, each linking to further displays, and you can add selection by job name or type, user, and more. Here, using the default options, we will see jobs sorted descending by CPU usage. The list shows jobs exceeding a minimum resource usage threshold, defined in the installation parameters. Smaller jobs are grouped by job type. For example, the second line here summarizes 3,106 tiny batch jobs. Per job, we see the number of collection intervals, CPU usage, job priority, IOs, and more. Pressing F11 takes us to the next screen. F11 determines whether or not to display an additional line showing job end time, memory pool, pages used, and peak interval values. Through the use of command keys to obtain further details, we have tried to make the software intuitive. We start our analysis by placing the cursor on the first job and pressing F9 to get the call stacks for that job. Often using a lot of CPU, a job call stack sample was collected, frequently. Here you see the first page. The columns show the initial program called the job status, and what we call the non-queue program, which is the last called user program in the stack. The currently active program is in roughly 90% of all cases an IBM utility, and most often an I/O routine. Following that, the 5 preceding programs in the stack are shown. Pressing F11 with the cursor on a line would show the entire stack at that point in time. At the bottom, A pink summary line shows job statistics for the active programs. Here, 45% of the runtime was spent by a single IBM program. To see the defined text, I press F4 with the cursor on that program. It turned out to be IBM's Retrieve Data Area, an old System 38 function that always triggers a disk access and therefore is very slow. We clearly see what the runtime is used for. However, unlike the automatic analysis, we are not advised if it can be optimized. Now you will see how use of F14, available from many GiAPA panels, generates a graph. Graphs are generated immediately in the IFS and can be configured to open automatically on your PC. The pie chart clearly shows how Retrieve Data Area consumed nearly half the runtime. Replacing this with a user space reduces total runtime by about 44%. Next, F8 has been used for a different job to analyze file accesses. It's possible to reach the details behind these summary lines by pressing F7 with the cursor on a file. As example, I have selected the file highlighted in the middle, opened for input only, and read 250 million times. I noticed in the call stack, not shown here, that the job only used key-based reads, and that the total of 638 million reads used 160 minutes runtime. The job triggered in 1,184 intervals, a hotspot, causing open file data to be collected. This makes our statistical analysis very reliable. The difference between the highest and lowest relative record number found is only 1,665. To sum up, the program used 250 million keyed reads on 1,665 records. That is nearly 40% of all the 638 million reads, meaning that 1 hour runtime could be saved by reading these 1,665 records into an array and using a binary search. GiAPA can often also solve unusual performance issues. A customer's chief operator was concerned because a transaction on occasion took 30 seconds to complete instead of the usual 1 to 2 seconds. Before the user could get hold of operations and they could start looking, the transaction had completed, so the root cause was invisible. The server seemed to run fine, never using more than around 90% CPU. Using the GiAPA menu option, including detailed data for all jobs, we only selected the 4 collection intervals around a delayed transaction. Checking the SMPO jobs storage management page out, we saw an unusually high page out activity. We therefore checked which job was allocating the most pages during those intervals. It was an SQL job creating a massive temporary table. That same job had also been running during other delays. Again, GiAPA had the data needed to find the culprit within minutes, another unique GiAPA example. GiAPA's SQL Observer should also be mentioned. It collects plan cache data for user-selected jobs at user-defined intervals. An IBM performance specialist estimated that GiAPA's automatic analysis can identify about 80% of common inefficiencies. Most of the remaining 20% involve SQL, where the optimizer's choice of access plan is important. GiAPA does not evaluate SQL access method efficiency, since IBM provides that function if the plan cache data has been dumped. Our SQL Observer automates that dumping. GiAPA's report on the dumped plan cache data shows where plans are stored, explains why a particular access path was chosen, and whether the optimizer changed it dynamically. The link shown is to a short video introducing SQL Observer. If you are interested, a free trial only requires a couple of hours to install and run. GiAPA software and documentation can be downloaded from our homepage. The free trial will give you 2 optimization recommendations, one for program code and one for file access, and show the estimated total for runtime savings. Thanks for your attention.